Today's lecture is going to be on the significance of sunlight. We're going to look at how sunlight is Earth's surface energy source. It's important that we carry over from what we learned last time. We learned that the Earth's axial tilt is influencing what locations receive the greatest amount of energy after a photon or light has traveled the 93 million miles, 150 million kilometers distance through space. A quick recap. We described the three modes of heat transfer as radiation, conduction, and convection. In this lecture, we're going to apply those. But first, we need to look at what sunlight in the electromagnetic spectrum is. Sunlight we describe and we think of as visible light. Visible light we describe as white, which contains all of the colors in the visible light spectrum. Your red, orange, yellow, green, blue, and violet. But it's simply just one little dot on the entire electromagnetic spectrum. The only thing that's different about these is that they have different wavelengths and frequencies. And therefore we can describe a wavelength from, say, that of a crest to a crest. These are larger or longer wavelengths down here in the radio end, and shorter wavelengths by the gamma end of the spectrum. Sunlight, or what we'll describe as visible light, heats the Earth as short wave or visible light as it enters our atmosphere, and then it heats the air above it from re-radiated long wave radiation that we describe as infrared. Infrared has a longer wavelength than visible light. Visible light is the only portion of the electromagnetic spectrum which our eyes interpret. It interprets each of them with different frequencies and different wavelengths. Red has the longest wavelength, and violet has the shortest wavelengths. So it means we got to go back and take a look at what's happening in the sun. And therefore, when we talk about light, we need to describe the life cycle of a photon, or light. Photons are born within stars, including our sun, as hydrogen is bound into helium, creating a high-mass element. Photons are the byproducts of nuclear fusion. Einstein showed us this as he described energy equals mass times the speed of light squared. It simply showed that energy and matter are the same thing. Because it takes 4 hydrogen atoms to be combined to create one helium nucleus, even though they have different masses, the different mass is now a new form. It's a new form of energy that we see as sunlight. But sunlight that we think of escaping the sun, it took a long time to get out. And this process that we described is called the random walk. Once nuclear fusion processes take place and photons are generated from matter, then they must migrate out of the sun. This is described as the random walk, sometimes referred to as the drunkard's walk. This theory explains how this is done. As a photon attempts to escape the sun, it must collide with matter on its way out of the sun's interior. So it has to be absorbed and then re-emitted each step along the way. Now you can pause this and read through here. But I just want you to realize that once sunlight is born, it doesn't escape instantaneously. It takes a long time. Not only a long time, it takes up to 170,000 years for the photons that we see reaching the Earth in which they were born. They were born roughly 10 to 170,000 years prior before they actually leave the sun and travel the 93 million miles to Earth. However, once that light is born, it travels through space and it reaches Earth. The electromagnetic spectrum, we're simply looking at light as pure energy. Visible light that enters our atmosphere has a shorter wavelength than the heat energy, or infrared, energy that is re-radiated back into space. Heat energy, or infrared, is considered to be long wave energy, longer waves than the original visible light. So let's apply that to the Earth. We're going to be describing the greenhouse effect. So think about it this way. We have visible light that enters our atmosphere. And some of that energy, about 50% of it, is absorbed by the Earth's surface. And some of that energy then gets re-radiated back into the space around it. Remember, we described the Earth heating from the ground up. So we're going to say incident or incoming sunlight passes through our atmosphere. The net incoming solar radiation is what we find the net that is trapped within the atmosphere. Insolation or incoming solar radiation reflects into some of it reflects back into space. But we're going to focus on the solar radiation that's absorbed by the Earth's surface. The sunlight energy coming in is then going to be re-emitted back into the space around it, and it's now going to be infrared radiation. This is absorbed and re-emitted by greenhouse gas molecules. And infrared radiation is re-emitted by our atmosphere. So our Earth is literally giving off heat. So we describe that amount of heat that's being re-radiated as called the Earth's heat budget. In this case, we have energy coming in, we have energy going out, and these are generally balanced. If the Earth system were balanced, the influx of heat would equal the outflow of heat. But greenhouse gases, or GHGs, are changing this equation to become imbalanced. The greenhouse effect. Earth naturally heats up, and that's a good thing. Liquid water. Water is a medium for complex chemical reactions. Like our Earth being a watery planet is very, very important for life. Earth's liquid water is believed to have played a key role in life's origins and evolution. So we're going to pay attention to this graphic here. We have sunlight. That energy reaches Earth. Some of it gets reflected back out into space. Some of it gets absorbed by the surface, and some of it gets absorbed directly by the atmosphere. So, well, what is the fate of incoming solar radiation? Well, light can do all sorts of things once it enters our atmosphere. It can be reflected or bounce off. It can refract or simply bend through the atmosphere. It can be absorbed. This increases the temperature of materials. And it can be transmitted. It simply just passes through. So let's slow down and look at insolation, incoming solar radiation. This is the amount of energy received by Earth. We could say that 20% is reflected immediately by clouds, 5% is reflected by dust, by other aerosols, particulates, and about 5% is reflected back by land and sea. So a total of 30% leaves the atmosphere. Whereas in this case, 20% of our atmosphere is actually absorbing. 16% absorbed by ozone, water, dust, 4% is absorbed by clouds. That's 20% in the atmosphere, and 50%, almost half of all sunlight, is absorbed by the Earth's surface. That's an important value we'll need to make sure we spend some time looking at. Of the 50% absorbed by the surface, 30% is re-radiated as long-wave radiation. The remaining 20% heats the atmosphere through conduction and convection, simply heat transfer processes. So if we look here, we need to make sure we realize that our atmosphere contains aerosols, and aerosols reflect light that's coming in. Remember, their aerosols are tiny particulates, dust, ash, sea salt, pollen, and microorganisms. These are airborne suspensions in our atmosphere. Aerosols can reflect, they can absorb, and they can scatter sunlight back into space, thus decreasing the amount of sunlight energy reaching the surface. So for example, Earth can have a short and temporary cooling period immediately after a volcanic eruption. As the ash travels around the Earth, it reflects sunlight back into space, almost like they're little mirrors. Eventually, the volcanic ash settles out of the atmosphere, and the climate recovers to what's considered normal conditions. But if we go back and look at how 50% of land and water absorb sunlight, they actually heat up differently. That the atmosphere is primarily heated by radiation coming off of the Earth. It's infrared. 50% of the energy is absorbed by the Earth and released back into the atmosphere. Thus, the temperature of air in a given location can be greatly affected by the materials found on the surface. Water absorbs vast amounts of energy from the sun. Likewise, bodies of water release this energy very slowly. And for this reason, areas near water are usually more mild. Because of water's ability to absorb, store, and release heat, the oceans of the Earth have an important role in helping moderate Earth's temperature. Literally, our oceans are like the Earth's thermostat. Different materials have different specific heats. You'll find that fresh water has a very high specific heat, whereas our atmosphere has a very low specific heat. Therefore, fresh water has what we'll describe as the greatest thermal inertia. Land heats up more readily and easily than water, has a lower specific heat. Land also cools more quickly than water. But notice not all land has the same color. This is kind of an idea of what's called albedo, the reflectivity of a surface. Albedo is a measure of an object's reflection of the sun's radiation. The measurement of albedo is a subjective scale, where 0 is for completely dark and 1 for completely bright. For example, fresh snow has an albedo of 90%, where 90% reflects back into the atmosphere. But coal has a refractivity of 0.1, or an albedo score, which just means 10% is reflected back. So taking this into account, all these different materials have different albedos. So some areas are absorbing and some areas are reflecting light. So light and dark surfaces respond to sunlight energy differently. It's a combination of all the albedos on Earth's surface that lead to an imbalance of heating. The imbalance of heat is what generates wind. So if I look at this picture, notice sunlight travels 93 million miles through space. It's going to reflect off of ice, but it's going to be absorbed in the asphalt. So different lightnesses and darknesses are going to have different albedo scores. So let's go back and look at what shortwave visible light and long-wave infrared or heat energy are. When you have incoming visible light, it's a shorter wavelength than infrared, and as a result, some of it's absorbed and re-radiated back with a different wavelength and frequency. So notice ice is going to reflect more, it's going to heat less, whereas dark surfaces are going to absorb more sunlight and actually heat up. So they're going to have different reflectivities, which we call different albedo scores. So think about sunlight as being pure energy. The greater the angle that reaches Earth's atmosphere, the greater the heat density, the warmer the conditions of that area that we're going to measure in watts per meter squared. That a greater direct angle is going to spread out that heat energy over a smaller area. And at some angle, that same amount of heat energy is going to be spread out over a greater amount. As a more direct sun angle, closer to 90 overhead, the greater the heat concentration. Areas where the sun is directly overhead is simply going to be hotter, and areas where it's more spread out are simply going to be cooler. And therefore, insolation or incoming solar radiation is going to influence the conditions of an area. Where sun is directly overhead, you're going to have hotter conditions. And where the area of the sun is spread out, you're going to have cooler conditions. By now, you should see how complex our atmosphere and its interactions with sunlight is. You should also recognize that much of what we study is described by the angle of insolation. The more direct the sunlight, the greater the energy, the greater the area receives. Greater angle, this is spread out over a smaller area, hotter. Lower angle, spread out over a greater area, cooler.